Given that the program is a database, it's easy to create tools that operate on programs. Because we like biological metaphors, we call these tools enzymes.
There is in IP a very useful enzyme that can extract a procedure from open code. We start by selecting a piece of code that we think might be shareable. We apply the enzyme and we get a procedure and a call to it with all the necessary parameters, formal and actual. It's too bad that the system cannot come up automatically with a meaningful name, so we have to supply that. Writing a new enzyme is not very hard. Using IP's powerful APIs and domain-specific abstractions, the lift procedures enzyme is only a few pages long.
The most important consequence of the IP tree representation is to create an ecology for new abstractions. This means that new abstractions of any kind can be added to the system and used right away. Because the abstractions are used to express the programmer's computational intent, we frequently use the word intention to mean an abstraction, a programming language feature, a definition in the IP tree.
We recall that to make an intention useful, we need to provide it with an identity, then describe how it should look, how it might be implemented, edited, and so on. Intentions can cooperate through parameters. For example, an if statement has its condition and the conditional statement under it as its parameters. In principle, any intention can have parameters, and any intention can be a parameter. It's up to the intentions to decide what combinations make sense. The implementation of an intention is described by a transformation enzyme, very much like the editing enzyme we saw earlier.
Let's now turn to a difficult technical problem. How can we create a system where separately written transformations can come together, operate on the same source tree, and produce a meaningful result? Paul will explain the solution.
At compile time, the intentions in a program must collaborate to build the desired target. The nodes in the tree have to make their contributions to this process in some order, and that order must be determined by IP. It's essential that information that any intention acquires will not be invalidated later by another independent intention. So, to ensure that IP can quickly find an order in which nothing is invalidated, the API allows an intention to ask for the minimal information it needs. A node can directly examine only its own structure. In order to learn more about its context in the tree, it will make stylized queries of other nodes connected to it. We call these queries questions. Questions are semantic in nature, since the semantics of a node is unlikely to change during the build, even as the tree structure is transformed. Examples of questions are, what is your type? Do you have a constant value? And most importantly, what is the lower level tree, the reduced tree, that constitutes your implementation? These semantic questions provide a means for portions of the tree to be abstracted away, yet still cooperate with the surrounding nodes. When an intention expresses itself in terms of other intentions, it can delegate questions to them. For example, a while loop might choose to implement itself in terms of ifs and gotos. Questions that the if can handle are delegated to it, saving the author of while the trouble of handling them. Some questions may still be intercepted by while, though. For example, a question about where to jump in order to break out of the loop. A strict rule for transformations is that additions to the tree are allowed, but deletions are not. If nodes could come and go in the tree, it would be impossible for IP to decide whether to report the presence of a node to an observer. By convention, all additions are visible to intentions that look for them, which means that observers must run after modifiers. The system maintains extensive dependency structures to enforce this rule. IP could not guarantee that any two intentions will work together, but it can detect incompatibilities and report an error. With carefully chosen questions, it will be possible for intentions to work together when it is meaningful to do so.
The benefits of intentional identity are clear when, for example, there's only one definition for an operator. But in case of generics, when there are several possible definitions for the same operator, the situation is even more interesting.
Making explicit what used to be implicit is typical to IP. A generic operator points to an archetype declaration that represents the abstract operation. This declaration is also a convenient place to summarize what is common among the diverse instances. The specializations of the generic procedure will be contributed to the archetype. These specializations could appear next to the archetype definition. However, the archetype is frequently found in a standard library that we cannot change, so we prefer to place the specialization separate from the archetype. The system will collect the contributions and select the appropriate instance for each generic reference.
We've seen how new programs can be created and edited in IP, but what about legacy code?
Abstractions of a legacy language, such as C++, can be defined as intentions. We can adapt a standard compiler front end to parse C++ text and create the intentional tree. This can be done for other languages as well. For example, for Java or for HTML. The preprocessor directives of C++ create some interesting challenges. It would not be a good idea to simply parse the output of the preprocessor into an IP tree, because valuable information would be lost. What we would like is to preserve the invariants represented by the preprocessor directives and express them intentionally. This can be achieved by a rather complex algorithm.
The results of automatic preprocessor intention recovery are very interesting. Let's look at a typical example.
Here we see a macro definition in the C source and a particular macro call with no parameters. After import into IP, we see the automatically recovered macro definition and the macro call. Note the two new parameters in IP. The first one appears because the original macro trickily referred by name to a local variable in the call's environment, a different variable in each call. The second parameter is the body of the loop that has been picked up by the sneaky syntax of the original macro.
In this case, IP did not just express the invariances of the original tricky macro correctly and without preprocessor actions, but it also made the undesirable dependency more visible and correctable. Similar results exist for if-defs, includes, and name concatenations. We've seen that IP can express abstractions from a wide variety of languages, from C preprocessors, C++, and other object-oriented languages. But even greater opportunities exist with domain-specific abstractions. Our example comes from the common domain of user interfaces.
This is an applet exercise written in Java that implements a simple paint program. I can use the applet to select a color, draw with the mouse, and clear the canvas for a new drawing. The interesting point is that more than half of the program text is there to implement the user interface. We mark this portion in red. The main goal of the code is to paint, of course. From that perspective, the interface is just some magic by which the user sets class variables, such as the pen color, or calls some methods, such as the method for clearing the canvas. Ideally, the user interface widgets that are used for this purpose would be completely separated from the part of the code that concerns itself with painting. Moving to IP, let us delete all the interface code and mark the declarations of the variable and the procedure which we think should be under user control. This mark is an intention that can be transformed to exactly the desired interface. Note, for example, that the transforming enzyme could automatically create the drop-down list from the enumerated type referenced in the declaration. If we now add a new color parameter to the clear procedure, we see that the interface will change accordingly. Incorporating the same change in the original Java source would have taken 25 lines, any one of which could have been the cause of a bug. When intentions are improved, all users benefit. For example, just by loading an update of the intention, the interface will be improved, in this case by the automatic incorporation of a color picker.
Java is a procedural language. Its statements describe how to do things. In contrast, many domain abstractions, including the one we've just used, are declarative. They describe what should be done. They're better because they're short and allow many ways of accomplishing the intention. By separating the intention from the implementation, improvements in the implementations become accessible to the programmers without having to change the program source.